Alright guys, hello. Today we're going to be looking at some proton NMR as well as some carbon NMR. We're going to start off with the carbon NMR for the molecule ethanol. I've taken the liberty of just kind of writing out the chemical formula and then kind of color coding our signals here, which we're going to look at in just a minute, and then kind of setting up a little bit of a table to just kind of get us off started. And I find that this really helps kind of keeping my thoughts in order, and it's really helpful to kind of look back at each of the signals and kind of list out all of the different parts, so then you can gain the most knowledge and correctly identify the molecules or correctly draw the structures as needed. So what we're going to start off with here is we're going to start off with the location for all of our signals. So we're going to actually start with A. We can see that it's at about 3.7 ppm, maybe 3.6. We'll go with 3.6 ppm. This doesn't have to be exact. It's just have to be kind of a guess and see like what region it's in. So then for signal B, it's just a little bit upfield from signal A. And what we notice is upfield is to the right, downfield is to the left. So when we say upfield, we mean it's a little bit to the right on our graph. So signal B is a little bit upfield, so I would say that's probably about 3.5 ppm. It's a little bit downfield from 3.5, but we can say it's about 3.5 because again, this is just kind of an estimate. And then we're going to move on to signal C all the way over here. It's way upfield at just downfield from 1 ppm. We're going to go ahead and call that 1.1 ppm. And so what this tells us is just a little bit about what type of signals we're looking at based on their locations. So we're going to go ahead and move on to our integral. What we can see from our integral is what we get with these 3H, the 2H, and the 1H. That tells us how many hydrogens are going to be exhibiting this certain signal. So for A, we've got 1H. For B, we've got 2H. And for C, we've got 3H. So then again, that just tells us exactly, like, generally how many hydrogens in our molecule is going to be exhibiting this signal. And so that can help us determine little bits and pieces of the structure and kind of like regional structure within the molecule. All right, we're going to go ahead and move on to spin. This is again related to the integral. And so what we can say, the spin for 1H is going to be 1, spin for 2H is 2, spin for 3H is 3. And that just tells us a little bit more about the protons, the hydrogens in the molecule and how they're oriented with one another. And then finally, we're going to look at our neighbors. So what are neighbors we can see from our integral as well. So if we know that let's say, we'll start with C on this one. So we know we have 3 hydrogens, so we know that there are going to be 3 neighboring molecules for this particular area. And then the same thing applies for 2. And then if we have 1H, you can almost always assume that it's going to be either an oxygen or an AOH group because you only have 1 hydrogen attached as a neighbor. So then you can go ahead and say that that's 1. And then from that, we're going to go ahead and make our guesses for what A, B, and C are. And we'll just start off with A. Since, like we said, it's most likely going to be an O or an OH. And from our ethanol chemical formula here, we can determine that it's most likely going to be an OH group. So we can just say OH is probably what that's going to be. For B, we can go ahead and take a guess that because there are 2 neighbors, we're going to go ahead and say that that's a CH2 group. And then so by default for based on our chemical formula again, we know that group C is most likely going to be a CH3 group. So then what we can do is we can go ahead over here and draw kind of a crude structure. So we have a CH3 group. So that's going to be looking like CH3. And that's going to be attached to a CH2. I'm going to go ahead and make that bond a little longer just for ease of drawing. And I'm just going to fix that a little bit. Go ahead and do that. We have another C, and this time it's H2. And then we have it bonded to an O, bonded to an H. Then we can go ahead and make this a little bit more of a simple structure. We have a CH3 right here on this bottom left corner, CH2 at this top right, so then we can create a bond, and we have an OH down here. So that is our structure for ethanol. We can go ahead and look back and see that we have two C's, which we needed. We have 1, 2, 3, 4, 5, 6 hydrogens, and we have 5 here plus this one, so that's going to be 6 total hydrogens. So that checks out, and that also checks out with what we have here. We have 1, 2, and 3, so we have 1 plus 2 plus 3, that checks out to 6 as well. So we know we have 6 hydrogens there, and then we have our 1 oxygen, which we can see there. So this all checks out. We can assuredly say that that is the structure of ethanol. Now we're going to go ahead and move on down to looking at a proton NMR, and specifically we're going to go ahead and take a look at the ibuprofen proton NMR. Again, we can go ahead and kind of color code these signals, but since there are so many in this case, I think I'm just going to label them. So we're going to start off with A, with B, with C, oops, this is going to be C, and then we got D, E, F, and G. This little signal all the way down here, this is going to be our solvent signal. So we don't have to include that in our analysis. It's just going to stay off to the side there. And then what we have here is we just have an enlargement of some of these, of basically B, C, D, E, and looks like A through E. So what we can just go ahead and do is we can say this is A, this is B, this is C, this is D, and that's E. And what that's doing is just giving us a better look at some of these more scrunched up signals so that we can better look at how many we're dealing with. So we're going to start off with signal A. Signal A, we've got a location of about 0.9 ppm. Signal B, it's about, I would say that's about 1.5 ppm. Signal C is about 1.8 ppm. Signal D is about 2.2 ppm. Signal E is about 3.9 ppm. Signal F and signal G are pretty close. This one's about 7.1, maybe 7.2 ppm. And then, so that's going to kind of give us just a better idea of where everything is located. That's just going to help us better understand a little bit about what we're dealing with here. So then we're going to go ahead and move on to what we know about the types of signals we're seeing. So that's going to be, we're going to list those off to the side here. All right, so for A, we've got 2 peaks, so we can go ahead and call that a doublet. For B, we also have 2 peaks, and we can reaffirm that right here. We can see that there's 2 peaks over there, so we can call that another doublet. For C, we've got 1, 2, 3, 4, 5, 6, 7 peaks. So anything really more than 4 or 5 peaks, we just call it a multiplet. So that's what we have for C, and then we can move on down to D, and D is a little bit simpler. We can see we've got, again, just a 2 main peaks, so we can call that another doublet. And then for E, we've got 1, 2, 3, 4, so we can call that a quartet. For F, looks like we've got 2 again, and same for G. Those are both doublets. So we can call those doublets. Alright, so what those words are telling us is just how many peaks there are within each signal, and that's going to give us a better understanding of how the protons at those signals are oriented in the molecule. And so then we can count. We have A is 1, 2, 3, 4, 5, 6, 7. And so we can see there that I'm actually going to just change this around quick. It's going to look a little better if we go 3, 4. So we know that we have 7 different proton signals. So there's going to be 7 unique orientations for protons in this molecule that we're trying to synthesize. So what we learn from that is that this is going to be probably a little bit a bigger molecule, because there are so many different types of proton signals. So what we can do is we can go through and kind of see that there's a lot of different signals. We can kind of deduce from that there's going to be a bigger molecule. And so that what we can then go on from there is kind of just taking a stab at what we think we can deduce. So then from there, we're going to kind of want to look at a little bit more about what we know about doublets, what we know about multiplets, and what that kind of signals for where things are going to be oriented within a molecule. And I am just pulling up a little bit of a chart for proton NMR to help me kind of work my way through this. And that's totally okay to do because there's a lot to remember. Alright, so now that I've got that up, it's going to help us a little bit to determine a little bit more about what we're dealing with here and how we can go about looking at this and kind of understanding how things work. Alright, so what we know from what we can see on this proton NMR chart is we can see that A is a doublet, B is a doublet, C is a multiplet, D is another doublet, E looks like it was, what did we just say that was? Quartet. And then F and G were both doublets. Alright. So then what we can determine from that is that we can also determine that there are these different numbers of signals, and what we can take from that is that we have a certain number of hydrogens that exhibit each of these signals. So that's what we're going to want to move to next. And the way we determine that is through kind of understanding where all of our signals are coming from, and it also helps to know the chemical formula. So what we're going to do is we're just going to write down the chemical formula for ibuprofen, which is C13H18O2. So what we're focused on here is the 18 hydrogens, and those are going to be split up among 7 different signals. So now what we have to do is we have to determine how many hydrogens are exhibiting each signal. So what we can do from that is we can use what we know about unsaturation, as well as what we know about the chemical formula of ibuprofen and we can kind of go through and like determine where everything goes. So what we're going to do is we see that we have, let's see, all right, so what we can do next is we can kind of go through and figure out the number of protons at each signal. And so we know that we have a total of 18 protons or 18 hydrogens over 7 signals. So now we have to go and figure out how many protons or how many hydrogens are exhibiting each type of signal. So what we can go through and do there is we kind of base it off of what we see on the graph, and we can kind of go through and just assign numbers to each of the positions. So I'm going to go ahead and start from right to left. So what we can see here, because we have a doublet, we know that there's going to be 2 hydrogens exhibiting here. Again, 2 more hydrogens exhibiting right there. Our multiplet, we're going to come over here. We see that there's at least 7 peaks along there. But what we know about our NMR is that there's only going to be 1 proton that's going to exhibit something like this, where we have a multiplet, so that we can say that it is going to be 1. And basically what this comes down to determining is the number of possible neighbors that you can have. And so we can kind of guess and say that there's going to be 1 hydrogen that's going to only exhibit something like a multiplet with neighbors. And this is another doublet, but it's going to be a further downfield doublet, so that's going to be coming in handy later once we look more at the type of structures we're going to make, and we can take guesses at that. So what we're going to do is keep moving forward. So what we see on D is we have 2 hydrogens again, so that's going to be a total of 4 hydrogens exhibiting there, but in 2 separate places within the same area of our molecule. They're all exhibiting the same, but there's going to be 4 of them. And then what we see at E is that there's going to be 1 hydrogen exhibiting a quartet. And then what we have left, we got 2, 4, 5, 6, 7, 8, 9, 10. So we have 8 left. So that means we're going to have 4 exhibiting at each of these. And then we can, from there, start to kind of take guesses as to what we're looking at here. So we're going to go ahead and go down here and write A, B, C, D, and then E, F, and G. So we're going to start over here with A. And what we can see with A, based on these peaks and kind of the location, is what we're going to have there is going to be some CH3 carbons. So we're going to go ahead and say that these are CH3. And then we're going to move on to B. What we can see from B is that those are going to be CH2 carbons. And so we're going to write CH2 or maybe even CH. We don't know yet for sure. And then we're going to move on to C. What we can see from C, that's going to be in a CH2. D, what we know from D is that it's going to be most likely it's going to be a CH, because it's going to have all those groups coming off of it. And then E, we can see that that is most likely going to be a OH group, just based on neighboring, and we know that there's 4 hydrogens exhibiting that, so we know that there's going to be at least a couple different OH groups, possibly more. And then F, we can also see that, or excuse me, there's only going to be one OH group. I looked at F and not at E. E is going to be one OH group because there's only one H. And again, one H, referring back to the other NMR that we did, we can know that with a 1H configuration, it's going to be an OH group or an O group. In this case, it's going to be an OH group. And then for F and for G, we can look at that and see that they are both going to exhibit the same kind of ideal signal. It's probably going to be a CH3, maybe an O, CH3, maybe an O. So then we can kind of start putting things together and just seeing where things fit. So we know that we're going to have a benzene ring, and the way that we know that is that there's 4 hydrogens exhibiting in doublet pattern. And so we can start off and draw our benzene ring. Start that off right here. And so we have the double bonds. And so what we see from our benzene ring is that we have 4 hydrogens exhibiting 2 the doublet signals. So what we can go ahead and take from that is that these signals right here are the same, and these 2 signals right here are the same. So that's 4 hydrogens, 1, 2, 3, 4, exhibiting 2 signals. Alright, so I'm going to go ahead and get those out of the way now. And we're going to go ahead and head back into our drawing. So then what we know is that we have branches coming off here and here. And we have some CH3 groups and some CH2 groups that we have to fill in. And the way that we can kind of figure that out is through our connections, as well as how all the molecules are oriented and their neighbors. So that comes into play with the spin and with the 1H and the 4H. We just kind of know that tells us how many neighboring protons there are. So we can kind of start to create our structure here from those different proton signals. So what we know we have is some CH groups and some CH3 groups. It's going to kind of look like this. And then we might have an O double bond coming off, and an OH there. And that's going to complete that side. And the way that we know that is we can see that through something like a proton NMR, that it's going to be oriented in that way. But or through a carbon NMR, excuse me, that we know that's going to be oriented that way. And also through the position of these signals, the downfield or further upfield tells us what kind of functional groups we're going to see. And again, I suggest pulling up something that labels and lists kind of the functional group locations in terms of upfield and downfield and ppm, because that's really going to help you understand where these signals are coming from and how we know that they're configured the way that they are. And so we can go ahead and move on to this other side. We know that there's going to be some more CH3 groups coming off of here and some CH2 groups. And so we've got some, looks like just kind of like a carbon chain with a methyl group coming off. And again, we know that through our proton NMR and through our carbon NMR more specifically. But what we can now check is if we have 13 carbons, 18 hydrogens, and 2 oxygens. What we can see here, I'm going to count them off. We're going to go ahead and do the carbons in blue, the hydrogens in red, and the oxygens in green. And we'll just go ahead and count them off one by one just to check. So with our carbons, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that checks out. We're going to go ahead and move on to our hydrogens. We've got 1, and this is a CH3, so we've got 3, and that checks. We've got 1 right here. got one right here, and then we've got some coming off of here on these. So we've got, let's move over to our other side first. We've got 3 here, we've got 3 there, we've got 1 there, 2 here. So that brings us to 3, 6, 9, 10, 11, 12, 13, 14. So we need to have 4 more hydrogens, and those 4 hydrogens are going to be located in the benzene rings structure. So then we can confirm that we have a total of 18 hydrogens. Finally, we have our 2 oxygens right there, pretty obvious. So that checks out. So, working through, kind of going through this whole proton NMR spectrum and kind of understanding where things are coming from, both in terms of like a carbon NMR, which you would see along with this normally, as well as this proton NMR. You can kind of see the number of hydrogens you're dealing with, the number of carbons you're dealing with in the carbon NMR, and the number of other molecules you're dealing with based on the position and spin, like the number of peaks, the position, and the height. And they all kind of play into how you can determine what your structure is. So what we have for our final structure then, I'm going to redraw it down here. We've got this double bonded, we've got that right there, and that goes into our benzene ring. All right, and then coming off the other side of our benzene ring, we've got that carbon chain with the methyl group, and that is going to be our final structure for ibuprofen based on our proton NMR. All right, guys, thank you so much.